Justin Marks on College Physics. We are going to do a nice little problem with some Kirchhoff. I like Kirchhoff. All right, so let's take a look at that problem and then proceed to do it. You ready for this? Sure you are. All right, so we've got ourselves a complex circuit that has 3 resistors, has 3 source potentials, and we're going to go ahead and solve it out. So we are given that R1 is equal to 100 ohms, R2 is equal to 200 ohms, and R3 is equal to 300 ohms. We've got the source potential 1 is going to be equal to 5 volts. The source potential 2 is equal to 13 volts, and the source potential 3 is equal to 15 volts. All right, so we've got that going on, and then we go ahead and draw out a diagram of what we have. So we go like this. Yeah, that'll be okay. Draw it a little like this. Do a little big. Down. It's supposed to be my resistor. And come up here and do go like that. So we'll take this to be R1, this to be R2, this to be R3, this to be potential 1, this to be potential 2, and this to be potential 3. So there we go, we got some circuit there. It's configured the way it's configured. And we want to go ahead and solve for I1 equals I2 equals I3 equals delta V1 equals delta V2 equals delta V3 equals. That's what we want to do, solve this all out. So kind of break this up into steps like, hey, write out the junction rules, write out the loop rules, and then solve for the currents and potential differences. The problem with just answering those in parts is that everybody could have different junction rules and different loop rules, but still get the right answer. Because ultimately the junction rule and the loop rules are contingent upon what direction you choose the currents to be, which we don't know. We don't know. So you know what? I'm just going to pick some directions. I'm not even going to attempt to make them correct. Actually, I might attempt to make them incorrect. Believe that? All right, so what do we got? I'm going to go ahead and say that we have this current in this portion here. I2, so it is going up like that. We've got a large potential there. Let's go ahead and say that this one, I3, is going up like that. And if those two are going that way, then, hey, let's just go ahead and say that I1 must be going like that. You may say, well, if you drew it exactly opposite of what we thought it would even look like, I could pick any directions. I could pick anything. So I'm just picking these. I got 2 junctions, J1, J2. Once I assign the directions of the currents, what do? Go ahead and apply the junction rule, right? Junction rule, J1. It says that the sum of all currents entering J1 is equal to the sum of all currents exiting J1. I2 and I3 come in, whoosh, I1 comes out. So I2 plus I3 must be equal then to I1. And ultimately, if we come down here, I1 comes in, I2 and I3 come out, and we get the same junction rule mathematically. So we just need one junction rule here for a 2-loop circuit. So then it's a matter of going ahead and utilizing the loop rules. But before we do that, let's just assign all the terminal potentials for all the elements in this circuit, as that makes things a little bit easier to keep track of. So we can go through the source potentials, littles minus, bigs plus, little minus, bigs plus, littles minus. And then for the resistors, we pick the direction of the current, or we correlate the direction of the current. Current goes from high potential to low potential. The current in this branch goes like this, so that has to be plus, that has to be minus. The current goes from plus to minus, it's going upward in this branch, so it goes from high to low, and it goes upward in this branch right here, so it's going from plus to minus. So the last thing that you want to do is reference what the potential terminals are for the sources and use that to guide you in the terminal potentials for the resistor. Don't even look at these when you're looking at the resistors. Look at the direction of the current. That's what's telling you what's plus and what's minus. So once we get all those terminal potentials, then we can go around and utilize our loop rule, right? So if I'm going to say that there's a loop number 1 and a loop number 2. I like to use the interior loops. If you want to use one interior and one exterior, it's fine. But for a 2-loop circuit, you need 2 loop rules. And what do we do with this? All right, so what direction am I going to go around my loops? I'm going to go around clockwise, because that's just what I always do. You want to do counterclockwise? That's fine. You want to do one clockwise, the other counterclockwise? That's fine too, which I'll show you here in a moment. But anyways, let's go ahead and look at loop number 1. And let's jump to this. L1. Well, that loop rule is going to be going around all these elements. There's 4 of them. E1, R1, E2, R2. So we need 4 terms that all add up to be equal to 0. So I'm just going to start here. We go from minus to plus. So we're going from low to high, that's plus. So we've got ourselves an E1. We're going from minus to plus across the resistor. So we got a plus, a delta V1. Then we come around, we're going from minus to plus. Plus E2, and minus to plus across this resistor, which is then plus as well. Plus delta V2. That's all 4 elements, have to add up to be equal to 0. Well, look at this. I can already say that something's chosen incorrectly because we can't have the 4 positive values all add up to be equal to 0. So that's okay though. It's okay. There's, we have to think about things later on, but nonetheless, that's what we've got going on for that loop rule. We come over to loop number 2. Loop number 2, I'm going to start right here with E2. We're going from minus to plus, from plus to minus. Plus to minus, that way gives us a minus E2. Come around, we go across this resistor from minus to plus, so we'll have a plus, that's a resistor number 3, so we've got delta V3. We'll go from minus to plus across this one, which will then be plus E3, and then we come around and go from plus to minus across R2, which will give us minus delta V2 equals 0. There we go, we've got our expressions. Got our junction rule, got our loop rules. Now it's time to solve. So how are we going to solve this out? That's right, simultaneous equations. So the first thing that we want to do is we want all 3 equations to have the same unknowns in them. We don't want a mixture of delta V's and I's. We want everything to either be delta V's or everything to be I's. So I'm going to make all the delta V's at the I's. That's the way I like to do it. If you want to do it the other way, that's fine. But we have, in general, that delta V is equal to I times R, right? So delta V1, that's I1, R1. Delta V2, I2, R2. Delta V3, I3, R3. That's it. So I can make that change here and say that the V's, 0 is going to be equal to E1 plus I1, R1 plus E2 plus I2, R2. And for this one, we got minus E2 plus I3, R3 plus E3 minus I2, R2. And that again, 0 is equal to that, so we're good there. All right, so now I'm going to cut this off here and say these are what we're going to use, along with that. Everything is written in terms of currents that we do not know, source potentials, which we do know, and resistances, which we do know. 3 expressions that involve the 3 currents, 3 unknowns being the 3 currents. Guess what? Yeah, we can solve for them all. exactly what we're going to do now. So let's just start figuring out what we want to do. This one involves all three currents. That's great. That's going to come in really handy because now we can write one current in terms of the other two. Both of these expressions only involve two of the three currents. This one involves I2 and I3, and this one involves I2 and I1. Both of them involve I2, but then they don't involve the same other I. So what if we change one of the I's, one of the currents, that isn't the same between them into two other currents that are the same? You say, what did you just say? Well, I've got this expression right here. I1 is equal to I2 plus I3. What happens if I say I1 is equal to I2 plus I3? I'll have an I2, an I2 and an I3, an I2 and an I3. Both of these expressions will have the two things that we do not know, I2 and I3, the same two things. That's exactly what we want to do. So we're going to go ahead and say, use this junction rule. Using I1 is equal to I2 plus I3 in L1 with rule 1. So what do we get? We've got ourselves E1 plus, well, now we've got I1, that's a quantity of the quantity of I2 plus I3 times R1 plus E2 plus I2 R2 is equal to 0. So that expands out. Fantastic. So what do we have now? We've got two expressions, two unknowns. What happens if we could use one of those other expressions to get one expression with one unknown? We can solve for that unknown, right? So that is what we want to do with this. I can take this expression and solve this out for something and use that something in this expression. Let's just go ahead and take this expression and solve it out for I3. I'm going to have one term of I3 in this new expression, one term of I3 here, and I can solve this out for everything else in terms of I2 and all the constants, and stick it in there. Sounds good, right? All right. L2, solving for I3. So what do? We just move everything over to the other side and then divide by R3, and we've got I3 by itself. That seems pretty straightforward there. I3 is going to be equal to positive, negative, positive, E2 minus E3 plus I2 R2 divided by R3. So we know what I3 equals in terms of I2. If we can figure out what I2 is, and we can figure out what I3 is. And if we know what I2 and I3 are, we know what I1 is. This is all coming together quite nicely, is it not? So now we're going to use this that in L2. So I'm going to expand this out first before I start embedding something else in there. So L2, I'm going to write as E1 plus, I want to distribute this R term through these two terms, just to make it a little bit easier to look at. Got I2 R1 plus I3 R1 plus E2 plus I2 R2 is equal to 0. And then we're going to stick this in right there. All right, so now we've got this. L2 says E1 plus I2 R1 plus I3 times R1. Well, I3 is this. So now we've got this quantity here. E2 minus E3 plus I2 R2 divided by R3. So there's I3 times R1. So that's this term right there. Plus E2 plus I2 R2 is all equal to 0. Wow, look at this. Constant, 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 constant. What don't we know? Well, there's three terms that have I2 in it. I2 is what we don't know. Can we isolate it? Heck yeah, we can. Now solve for I2. So, it's helpful to have this all expanded out and actually do this all symbolically. We could add some terms together and kind of get some numbers in here. Anyway, I'm going to do this symbolically for now. We'll put some numbers here shortly. But we've got this. I'm going to expand it out first, distribute this through so we've got all our terms together, and then we can go ahead and isolate our I2. So we have E1 plus I2 R1 plus E2 R1 over E3, E2 R1 over R3, and that's working on this. E2 times R1 over R3 minus E3 times R1 over R3 plus I2 R2 R1 divided by R3 plus E2 plus I2 R2 is equal to 0. I2 term, I2 term, I2 term. I'm going to throw everything else onto the other side except those three terms. And we have ourselves I2 R1 plus I2 R2 R1 over R3 plus I2 R2 is equal to, well, all these other terms are going to go over to the other side, so we'll have minus E1 minus E2 R1 over R3 plus E3 R1 over R3 minus E2. All right, and what could we do finally? We could factor out I2 over here. Write this then as I2 multiplied by the quantity of R1 plus R2 R1 over R3 plus R2 is equal to negative E1 minus E2 R1 over R3 plus E3 R1 over R3 minus E2. Then what could we finally do symbolically? We divide both sides by this quantity. And we've got ourselves I2. So I2 is equal to the quantity of negative E1 minus E2 R1 over R3 plus E3 R1 over R3 minus E2 divided by the quantity of R1 plus R2 R1 over R3 plus R2. Whew, look at that. Took a little bit of algebra, not that big of a deal though. What can we do with this? Can we calculate this out, huh? Because we know these are just a bunch of numbers. Let me get my calculator really quick because I put it down. Whoosh! All right, so I'm going to do this kind of term by term here. We've got ourselves I2 is going to be equal to minus E1. So we got quantity minus 5. Put a little, not getting in the way, blockage there. Minus 5. E2 is 13, E3 is 15. And I'm leaving out the volts and ohms here. I'm not going to worry about that. 13 times 100 divided by 15 to R1 over R3 plus 15 times 100. Oops. Already messing this up, huh? I'm looking at that one and I'm writing this one. Divided by 300. 13 times 100 divided by 300 plus 15 times 100 divided by 300 minus 13. And that's just the numerator. Let's just calculate that out really quick here. Negative 5 minus 13 times 100 divided by 300 plus 15 times 100 divided by 300 minus 13. And I get negative 17.333. Negative 17.333. And then, of course, we've got this bottom part. We've got, it's going to be divided by 100 plus 200 times 100 divided by 300 plus 200. And that is going to be that divided by 300 plus 100. This is 400. 300. That doesn't seem right to me. 100 plus 200 times 100 divided by 300 plus 200. Yeah. All right, 366.667. 366. I'll just say 0.6. All right. 200 times 100 divided by 300 plus 200. So what do we get with this? I2 is equal to negative 17.333 divided by the 366.67 gives us negative 0.04727. Negative 0.04727. This would be amps. All right. It came out to be negative. Let us just keep going. You know, we got I2. Let's find out what I3 is based upon this I2, and then we'll discuss some things here. So how do we get I3? Well, once we know I2, whoosh, come back here, because we have I3 written in terms of I2. So from that, right there, we can write ourselves that I3 is then equal to E2, which is 13 minus 15 plus this, which is negative 0.04727 times R2, which was 200 ohms. And that's all divided by 300. So we'll go ahead and calculate that now. We got 13 minus 15 minus 727 times 200 divided by 300. This turns out to be negative 0.03818 amps. Negative. All right, then lastly, what do we got? Well, we've got that I1 is I2 plus I3. I1 is equal to I2 plus I3 from the very beginning. So what's I2 plus I3? Well, it's that plus that. It's like negative 0.7, negative 0.8545. Let's make sure. Answer minus 8545. Negative 0.08545 amps. There we go. Well, we got negative currents. What does negative current mean? Negative answers. The wrong direction was chosen. Or the current. Oh no, we picked all the currents to be in the wrong direction there. Shoot, everything's wrong. That's not true. Everything is right except for the direction. These numeric values are the currents. Take away the negative sign, switch the direction that they actually are shown in the diagram, the direction that we picked, and you've got the correct answer. So the values are correct. To make them positive. And we just know, hey, you pick something in the wrong direction, you're going to get that that current ends up being negative. So in this case, pick them all wrong. Is it possible just to pick one wrong? Yeah. You get one wrong, that's okay. You still work through it. Don't change things in the middle. Notice that I didn't say, oh, I2 came out to be negative, I'm going to make it positive because I chose the wrong direction. You switch directions in between, you've switched all your rules. Junction rule changes, the loop rule changes, and all your equations that you've done before don't apply anymore. Work through what you have. Work through what you have until the very end. You got all the currents, and then you can go ahead and say what was chosen in the wrong direction, what wasn't, and the values, the absolute values of what you calculated them to be, those are correct. So ultimately, hey, you get all the currents, all the potential differences just follow out of that. So I'm not even going to calculate those, but the potential differences, we just got that delta V1 is equal to I1 R1, delta V2 is equal to I2 times R2, delta V3 is equal to I3 times R3. You can always go back once you have all the potential differences and currents solved for and make sure that they do correlate directly with the loop rule and the junction rules, as they should. Got to be careful with the plus or minus though. These expressions here, as we have them, have the signs that we've developed in answering things. So you've got to be a little careful. But anyways, the main point is to be able to get the currents. If you get the currents, everything else falls into place. Directions, everything. Good times, right? Good times indeed. Gotta love Kirchhoff. Thank you, Mr. Kirchhoff. Have a good day, everybody. Peace.